This is Lab 3, Black Hole. In this lab, I created a computational model that showed a star orbiting around a black hole, and I analyzed the star's motion with knowledge of the star's mass and the black hole's position, but no knowledge of the black hole's mass. As you can see, the objectives of this lab included analyzing the star's motion and trajectory around a black hole and calculating the net force acting on the star. Additionally, I needed to determine the black hole's mass after calculating several known and unknown factors of the star's motion. To calculate these objectives, I used the momentum principle to relate the change in momentum to the net force while assuming that the gravitational force is the only force occurring between the two objects. Before beginning the lab, we learned in lecture that the momentum principle says that the change in momentum is proportional to the net force times delta t, and because of our knowledge of vectors, we know that the momentum and the net force will point in the same direction. The momentum principle is very helpful for this lab because we can break up the net force into its parallel and perpendicular components, dp over dt parallel and dp over dt perpendicular as shown below. When we do this, we also obtain a parallel and a perpendicular net force, which is extremely helpful because dp over dt parallel tells us if the system speed is increasing or decreasing, and dp over dt perpendicular tells us if there is any change in direction of the system's momentum that will lead to any curvature we may see. Here we can see the heart of the lab. To the right, we can see the star in yellow, the black hole in black, and the star's elliptical orbit in green. The system is the star, and the surroundings is the black hole and the universe. And the only force acting on the star is the gravitational force acting between the two objects. Also, the star's mass is 2 times 10 to the 30th kilograms. The black hole is located at the origin, and we are measuring our data in time intervals of 1 day. When creating the computational model, I set the initial conditions highlighted in blue, such as defining the star's mass and the black hole's position. Also, I iteratively created a list of all the x and y values obtained from the velocities calculated, and used a while loop to calculate the displacement and velocity of the star, and I advanced the time by delta t after each iteration. To calculate the net force, I first calculated the list of initial and final velocities and found the initial and final momentum by multiplying the star's mass by the initial and final velocity respectively. Afterwards, I calculated dp over dt by dividing the change in momentum by the change in time, and because of what we learned earlier, dp over dt is equal to f net. Like we said before, we need to break f net into its parallel and perpendicular components to calculate f net successfully and accurately. I did this by first calculating dp over dt parallel, which involved calculating the direction of the momentum, p hat, and calculating d magnitude, p over dt, and I multiplied these values to obtain dp over dt parallel, as shown in green. Because we know that the sum of the parallel and perpendicular components equals dp over dt, we can find the difference of dp over dt and dp over dt parallel to calculate dp over dt perpendicular, as shown in black. To calculate the black hole's mass, we need to take the net force we calculated into account and set it equal to the gravitational force acting on the star using the gravitational constant, and rearranging this equation to solve for the black hole's mass as shown in the code and below. After running the code in GlowScript, we can see the star's orbit at 4 different times. In the animation, the orange arrow represents f net, the magenta one f net perpendicular, and the cyan one f net parallel. Below, you can also see the magnitudes of each. One thing to notice is that f net is always pointed toward the black hole because of the gravitational force only acting between the two objects, and also f net perpendicular is always pointed inward to the kissing circle, and both f net and f net perpendicular have larger magnitudes the closer the star is to the black hole, which follows the law of gravitation, in which gravity is greater at shorter distances. Also, you can see that f net parallel is always parallel or anti-parallel to the star's motion, which causes the star to either speed up or slow down. At the bottom, you can see the average black hole mass that we calculated earlier, which is 1.44 times 10 to the 34th kilograms, and you can also see the standard deviation. From this, I calculated a coefficient of variation, which is extremely small, which means my calculations for the black hole mass was very accurate. The what does it mean question wanted me to talk about how net force and its parallel and perpendicular components differ from the rate of change of momentum and its components. The two and their components have the same direction, but there is no real difference between the two, other than how they are calculated, such as taking the sum of all the forces interacting with the system to calculate f net. But f net is the cause, and the change in momentum is the effect that we see in the system. Lastly, the what if question asked if I could calculate a new black hole's mass if it replaced the original black hole, and I could because the star's orbit would change due to the different gravitational force it exerts, since mass plays a role. So I would be able to determine the difference in the star's orbit and calculate the black hole's mass. But nonetheless, this lab accurately shows Newton's second laws at work, and it showcases how it is useful for motion in which the momentum changes. Thank you.